Good morning and good afternoon, as it is afternoon for me, and thank you all for attending my talk on reinforcement learning for traffic flow management decision support. Before we begin, I would like to thank my co-authors, Eric Fargo, Emily Bromberg, and Everett Carson. In the interest of bandwidth, I'm going to turn off my video screen as well. Next slide. As we all know, air traffic management is a large, interconnected system that operates at multiple geographic scales and is driven by the needs of a diverse set of stakeholders. As we look towards the future, these complexities will only increase. New entrants with advanced operating paradigms necessitate that the ATM system evolve to support more efficient and adaptable services for both our traditional and our new stakeholders. Please click. Automation is key to this future, and recent advances in artificial intelligence and machine learning hold promise for addressing the complexities of the operation. We are all aware of the successes of Google's DeepMind in winning complex strategy games such as AlphaGo and AlphaStar. However, the main question is whether these successes can be translated to support the challenging and intractable problems faced in ATM. Air traffic flow management, or ATFM, which involves the design of management control actions, such as ground delay programs at longer look-ahead times, where there is a high degree of uncertainty, and this is a key challenge in the operation. ATFM is a multi-stakeholder process where stakeholders have varying and potentially competing objectives. The collaborative decision-making process is informed by a wealth of data from weather forecast, traffic demand, and some automation to support future predictions. However, even today, decisions are still fundamentally based on experience. As the planning aspect of ATM, ATFM supports safety, but is not itself safety critical. As such, we believe it provides an ideal candidate to develop and mature these complex technologies and leverage them to solving the current and persisting challenges. The ATFM problem, no, we're great. This is perfect slide. The ATFM problem we focus our initial attention on is the design of traffic management initiatives, or TMIs, to manage arrivals into the Atlanta airport. This problem was chosen as it is sufficiently complex to investigate the timing of TMIs under different degrees of uncertainty, while being tractable from the standpoint of both simulation time and interpretability of the results. On the right, you see ATL abstracted into a 4-corner post configuration, which is typical of the operation there, where in addition to the airport resource in the center, we define 4 corner post resources, which you can see labeled as Northwest, Northeast, Southwest, and Southeast. Please click. Historical traffic is mapped to these 4 corner posts, providing a schedule of demand. For the purposes of this initial experiment, we will consider this demand to be deterministic. Please click. Each resource has an associated nominal capacity, which may be further reduced by weather. So we can see our Zeus is our little weather demon over there trying to complicate the operation. Specifically, the most common airport configuration for Atlanta provides the baseline capacity of our airport arrival rate, or AAR, and the associated meteorological conditions determine its reduced rates. For the corner posts, an analysis of the 95th percentile historical throughput in the quadrant defines the nominal capacity, and a 2D coverage model at the 80 nautical mile quadrant provides the reduced capacity rates. To get forecasts of these, to get the forecast variables that help us determine, that we use to determine the capacities, we use the short range ensemble forecast, which is generates our capacity scenarios. Note that there are 26 members in the SHREF, and so therefore we are left with 26 capacity forecasts. Together, the capacity forecast and the demand schedule provide our historical scenario, which is then provided to the TFM agent, which may take click, no action, click, or may instead decide to take a ground delay program, or GDP. If this is chosen, the agent must decide decides to take a GDP. The agent will have to also specify the start time, end time, and rate. The GDP will delay flights on the ground at their departure airports, and the result will have TMI-induced ground delay. In addition to or instead of, the TFM agent can assign a metering TMI to any one or more of these corner posts, and that the assigning of the metering delay will incur TMI-induced airborne delay. And for each of the metering actions defined, the TFM agent must specify the start time, end time, and rate. Please click. When the TFM agent decides an action, this action is then changes the demand schedule prior to arrival at these corner post fixes. So when we get to the part where we're actually looking at the effect of these TMIs, we have a queuing model that represents the propagation of demand through the 4 corner posts and then to the airport. The rate or the constraint on each queue is actually determined by a nowcast, so that we have the observed or actual, which we will call it right now, in terms of the way the method is going, the way that we're using the same method across all the different capacity reductions, but we're using a different set of information. The queuing delay corresponds to the ATC-induced airborne delay. Please continue. So how does the TFM agent decide upon which action? The answer is through exploration using a heuristic search process known as Monte Carlo tree search. At its essence, Monte Carlo tree search has 4 steps. The first is to select a state action, state or an action to explore. Where the state in such a game as Go refers to the available board positions from the current position shown as the root node. Second, and please click, is to continue expanding future states, where greedy selection is employed to build upon promising actions as measured by a reward function, but also tempered with random exploration to better fill out the tree. Third, please click. The third operation is referred to as a rollout, which plays through the rest of the game, in quotes, to acquire a score, and please click. The fourth step is to back up this score information to previous valuations. Please click. This process continues by selecting new state actions to explore, and again, updating the valuation of these target states. Next slide. The key to our approach is enabling the TFM agent to evaluate potential actions under the different forecast features provided by the capacity forecast. As mentioned, we're using the short range ensemble forecast, which has 26 members, and therefore 26 time series of capacities are generated for each of the 5 resources. Please click. Our unique design begins by partitioning this capacity ensemble based on the forecast similarity over all resources for the hour, where at future times, these groups may subdivide based on the next hour similarity. As you can see from the figure at the right, we have 2 different partitions at the first time step, but as the future, that first partition is partitioned further. The tree is constructed assuming no action is taken at any point, and the rollout uses the queuing model that we just described to calculate the cost or reward associated. By initializing the tree in this manner, we ensure that if the TFM agent recommends a TMI action, then the expected reward associated is better than doing nothing at all. Finally, after this process of building the initial tree, the Monte Carlo tree search continues to expand upon other actions using a 2-step process where it first selects the state and then selects from which weather forecast or capacity forecast it's going to sample, and then picks different actions to sample from them. So the analogy with the Go game sort of is a little bit different here, because we have to sample both state and action separately, because this is not strictly a Markovian process. Moving on to, I keep mentioning this reward. So what are we talking about in terms of the reward? So capturing the correct reward function is obviously that's something that requires is an ongoing effort of research to understand how the multi-stakeholder process can be translated into a reflective set of goals or reward function. Right now, that is outside, for up until this point, this has been outside of our initial consideration, though we are hoping to use the model that we're generating here to actually advance that research. But for here, and for this work, we chose to capture simple but nonlinear accumulation of delay, which we've termed delay impact. While this is obviously not an adequate representation of all these considerations, the above function was constructed with SME input to ensure that some of the critical sensitivities between TMIs and traffic impacts were represented. Here we have the three types of delay. We have ground delay shown in blue, showing the highest impact when delayed minutes are really small. So we have an inset into the plot here, so we can see the little bit of the details of the small numbers of minutes. But after about 10 minutes per flight of delay that has to be absorbed, that becomes actually the least impactful option. Metering delay is in orange, and again, starts off with a lower impact than ground delay for the same number of delay minutes, but then around 10 minutes becomes a bit higher. And if we note from the larger graph that at 30 minutes, there is a step function increase in the impact associated with the delay to account for the increased likelihood of having to divert a flight at these longer airborne delays. Similarly, ATC delay, shown in magenta, occurs when the demand and capacity imbalances are resolved only within the TMA and therefore by the queuing model. It is the least impactful form of delay for up to 2 minutes, but quickly becomes the highest impact for delays as highest impact delay as TMI actions would be preferable for longer disruptions. Please continue. So we have our overall process here. Our goal is to generate TMIs in real time. To demonstrate this, the real-time response of the TFM agent, we allow the Monte Carlo tree search to explore possible TMIs for the next hour for 1 hour, where the result at the end of that hour is the action that will be taken for the upcoming hour. And if we look at the types of TMIs, we have the ground delay program and the metering program. But as I mentioned, we have to have the TFM agent has to set the actual parameters for start time or offset here. So that's the difference between the time at which the action is recommended and the time it would actually be initiated. The rate and the duration for each of those. For the GDP, we just use an all scope definition, and for metering, that scope does not mean anything. So even with just a few parameter options for each of these settings, we have almost 75 million options per time step. And we allow 1 hour for the exploration of which actions to take. Next slide. So what we've done to baseline this process is we've actually I'm sorry, can we go to the previous slide? I got a little ahead of myself. What we've done is to compare the TFM agents' actions under forecasted information. We also ran the same scenario, the same process you see on the right, except that the TFM agent was provided the exact information, the capacities that will be in effect in the queuing model. So in that case, it has perfect information, or as best as we're using that terminology here. So we can go to the next slide. Thank you for letting me clarify. And so we executed this experiment for 3 non-consecutive months in 2019. Choosing non-consecutive months to be able to capture a variety of different forecast observed conditions. And if we look across these about 90 some odd days, we see that the agent is able to find a solution with similar delay impact as when provided with perfect information. So the blue dots are with the forecast information and the orange dots are with the observed capacities. So obviously we expect in some cases when there is a lot of variation in capacity that we're not going to have quite as close of an adherence, which is to be expected. But overall, we see that it's relatively matches the pattern, becoming relatively close. We want to, before I explore the 2 days highlighted, June 8th and June 10th in particular, I will note that the June 22nd day looks to be an anomaly in something that happened with the simulation. I think the simulation ran out of time. So both of the shref or the predicted information are showing really high delay impacts. So we're still figuring out what exactly happened there. But on the other days, we can see that we have a response that's a little bit more normal. So we're going to actually start with the June 10th day. Please advance the slide. Here we can look at the hourly delays by type, where we have, again, the ground delay in blue, the air delay, TMI air delay in orange, and the ATC impact in red. And what I want to highlight is the particular GDP on the top, where we have actually 2 GDP actions were taken. The first sets an initial rate and start and end program. But before that, just as that program is actually starting at hour 9, the decision is made at hour 9 to actually increase that rate. Now, if we look over on the right of the forecast, what we have here is the 26 capacity values for each of these resources shown as the colored lines, and then the actual capacity that was actually used in the simulation. And if we can go up and look around between hours 6, 9, and 10, we start to see that, especially for the airport, that the capacity predictions are a little bit lower than what's actually being observed. We're actually getting close to full capacity, so that as the Monte Carlo tree search is actually, evaluating possible new actions, it determines that a revision to a higher rate is a better decision. So this is the kind of adaptability and response we hope to show with the TFM agent. If we go to the next slide, we're going to go back to June 8th. And here we see that we have a huge spike of delay impact around hour 6. And that's primarily due to a large amount of ATC delay. So very few TMIs were being used, but there's a lot of congestion. So if we look now at our capacity forecast on the right, we see something a little strange. For the Northeast and Southeast forecasts, the black line is far below any of the capacity predictions. By having the ensemble outside, by having the observed information outside the ensemble, the TFM agent is unable to react to this impending congestion, and therefore is unable to really manage that ATC air delay well, or that congestion well. Okay, so I want to move to the next slide. So those are a review of the results that are in the paper, but I'd like to spend some time talking about both some aspects of what we've learned from this process, as well as how do we start to, move forward with this technology for addressing these difficult real-world problems. So let's start with some observations from the results. The first is that as we just mentioned, is that the agent's reliance is on the forecast, which enables the agent to adapt the strategy based on feedback from the evaluation. But it can also lead the agent astray when the forecast doesn't represent the observed data. So one challenge of the SREF is that the new forecasts are made only every 6 hours. But other ensemble products have higher refresh rates, which might alleviate this problem. Similarly, a technique termed data assimilation that could be incorporated to actually update forecast probabilities in between the actual official forecast updates. But fundamentally, if the forecast is not showing information that is captured, this represents the actual ongoing, observed information, is going to be a lag. Now, that's the cost of uncertainty, and we all know that. But the better we can, reduce that lag of that time, or the amount or the severity of that difference between the observed and the forecast, the better these types of agents will work. Second is that the second issue is to define performance. So again, we talked about what is, we used a baseline of perfect information. Now, the other option is that I could, as we talked about, the tree is built with having only no action. But at the end of the day, that provides basically an upper and lower bound, because we know that some action is going to be taken, but how do we actually measure whether or not the action is a valuable action? More than so than just assuming perfect information or no action. So What you really want to do is obviously have SMEs define that the expected performance, the actions generated and the resulting outcomes match their internal expectations. But to do so brings us to our third issue, which is to have appropriate metrics. Here we used a delay impact because it was something we could define relatively easily, and it did capture some of the sensitivities between the delays and how that impacts the system. But as TFM is a multi-stakeholder process, there is a wealth of research proposing different methods. But we still don't have a defined set that can be formulated to be sensitive to a real-time decision environment and capture the range of considerations that define a good strategy. This is especially important, and it may actually result in slightly different metrics when we consider that for the agent is not actually just assessing its past performance, it's trying to actually learn how to manage demands, capacity, imbalances while also interpreting the forecast information in real time. And so finally, what we showed here was a real-time application, 1 hour for decision of the next hour's information. But our test case was relatively small with 75 million decisions per time step. Relying strictly on Monte Carlo research to evaluate these range of options quickly to come up with a good action is not necessarily scalable. So we need to think about how do we move towards something that's a little bit more robust. And that brings us to our next slide. So in this, looking at the lessons of AlphaGo, you can go click through one more click just to get the things completed. We look to the successes of AlphaGo. Here, they use the Monte Carlo tree search algorithm as the last step in what was actually a 3-step process, where the first step entails the creation of an initial expert policy from historical data. And then where this expert doesn't have to actually be particularly successful in that it is just an initial step to a deep reinforcement learning process where the agent learns from trial and error. And so the combination of all 3 processes is what give AlphaGo its strength and its success. So we go to the next slide. But as hard as it is to win Go or StarCraft, the TFM problem is just much harder. First, which has nothing to do about TFM, this has to do with the fact that most of our working environments are not equipped in the way that Google's DeepMind is. That if MITRE were trying to actually solve the Go problem, given the disparities in the computational, the hardware and available, that you're talking about, while they were AlphaZero actually was able to use 5,000 TPUs, tensor processing units, to solve AlphaZero in 13 days. Our access is to 34 GPUs, and even if we assume a GPU is equivalent to a CPU, which it's not, that would put us at about 1,900 days to actually solve Go. But beyond the hardware is the challenge of the problem at hand. So first click here. Our action space might be over 74 million per time step, which results in about 10 to the 189th possibilities. Go is 10 to the 761st. However, our state space is even bigger challenge because we have to capture both the forecast, 26 members on ensembles of 15-minute capacities at 5 resources for the entire day, and the traffic. And again, unlike Go, the Markov assumption for our board states does not hold for TFM. Thus, we cannot assume any state, but must actually simulate the state forward at all times. So that makes this problem a lot bigger and harder to solve. The second thing, please click, is despite having generated 5 years of scenario data, 1,825 days for Atlanta, the majority of these days are clear weather. In fact, only about 200 days have measurable capacity reduction, and only 80 days with historical GDPs. Excluding the 3 months of data we use here for testing, we have only 55 historical days with GDPs out of the rest of the 5 years. So while this impacts our ability to sample in both the supervised learning expert policy definition, but also in the deep reinforcement learning model. To give you an idea, AlphaGo had 160,000 historical games to learn. Another aspect that was used, please click, is this idea of another of ways that they achieved successes was a self-play, playing against each other, playing against other games that they have generated to actually get better at winning. But this is an analogy that doesn't really work here because the weather isn't trying to win. So while we start to look at the not being able to play against the computer version, this is a little bit more aligned with what the Alpha Star had to do, but they then relied even more heavily on expert policy, which again, we've just discussed as a problem. And finally, one of the last challenges we faced is the accurate representation of the game. So when Google is representing the rules of, Google DeepMind is representing the rules of Go to the agent, they're representing exactly. Our queuing model is far from an exact representation of the airspace, but it does run a 24-hour day in about a second. And that's the kind of time, the speeds we need. So the question we are left with is, can we use a simulation that takes a second to run an entire day simulation to learn a policy that is valid and viable policy and what will be either measured in a higher fidelity model and ultimately the real-time operation. So the final slide, basically, I'm just kind of summarizing that we were able to do use Monte Carlo tree search for real-time context, and we showed that we were able to actually generate TMIs under, in both uncertainty and with perfect information, and we see that the method shows promise. But in order to provide a useful decision support capability, the ability to generalize is key. What are the best methods for generating a learned policy? What are the limitations given the forecast uncertainty? These are the research directions we need to all be looking at for how we can move forward with this research and actually deliver on some of the challenges and opportunities that were highlighted in the vision for next gen that was shown in the so, and then I totally liked on the word. And then anyway, so, and then obviously the other takeaway is data is key. So I'm going to leave it with that and open up for questions.
Thank you very much. The way to do questions, I believe, in this conference we're trying is to use the Q&A function in Zoom where you can type your question in. Or I think it's also possible for you to jump in with one. We have 54 people in the room. That's not too many. Anyone have any question to kick off a discussion?
So Craig, only people, presenters have the opportunity to talk.
Okay, so you have to type it. Yeah.
Yeah.
Okay. Okay, then I will ask you to elaborate on maybe a little bit on what things we've tried on slide 12 to try to add those other elements into the decision spot. I mean, there's the computational limitation, obviously. There's the data limitation. What are the options going forward? What kinds of things can we try to do to gain sort of the historical context?
So one of the challenges we saw, I mentioned this little problem had 75 million design parameters, right, per time step. And so 55 days is not going to give us an understanding of what that is like the most underdetermined system, right? What we've learned is that one of the other challenges with trying to just leverage historical data to understand how you could, say whether or not to have a GDP and then what parameters to be using is actually that the computation, the large part of the decision space is the TMI parameters themselves, as opposed to the decision to have or not to have a TMI. So what we've done is actually use Monte Carlo tree search to try and basically create synthetic data, looking at allowing the tree search to actually define, a certain amount of time to actually select an action and what would be those parameters, and provides, a lot of different a lot of different sources of information to actually initialize a neural network. But basically, you're not actually leveraging that historical data. The other thing we were trying to do to actually, again, create more synthetic data and more samples in general is to translate weather from nearby areas of the airspace over Atlanta. Now, we don't want to just create fictitious weather because we're not going to necessarily capture the right dynamics, and that's an important part for the agent to learn. But by translating weather from, say, airports in other places in Georgia or Mississippi, and actually taking all the forecasts and terminal information and then prescribing it over Atlanta and looking at what the TFM agent would do under that forecast information, could provide additional data for the learning process. But essentially, we basically don't have an expert policy that we know of. We are going to, the only other way we can think to do this, actually see if it's generalizable across airports. And that would be the only other way, is that you start to get enough information across different airports. And the value of that would be that you only have to do this once. But it's unclear whether or not it's going to actually be enough if you're going to have, if it's just going to end up being noise effectively.
Okay. Okay. We do have a couple of questions in the Q&A from Nitesh Manikoth. One is, what did you say were your options to reduce the parameters?
Design parameters?
Yeah, I guess.
Yeah. Oh, okay. So the state space. Okay. So, okay. I mean, so obviously we don't want to necessarily reduce the parameters. We actually want to make more parameters, right? We want something that is robust to having the opportunity to actually be really, really kind of nimble with the use of TMIs. But what we need to do is think if we can actually represent the problem in a state space that's smaller. So right now, for example, we're using just again, forgetting about uncertainty and demand, we have 26 forecasts of capacity. What if we could actually make those smaller by understanding some of the dynamics about them in advance? So one option we looked at was, say, principal components analysis as a way to actually make that design space a little bit more tractable. Another thing we're trying to explore right now is, is there structure that we know from the geography that we can actually leverage some network theory about how to better represent this information in a more tight and compact manner, because fundamentally the fewer design variables or the fewer states and state information we provide the agent, the easier it is for them to learn. But the goal, the challenge, the balancing act is that by abstracting it too much, we take away the parts of it that we're trying to learn. So we are, trying to see if we can identify, representation mechanisms for caps that still capture the sensitivities we want while becoming a smaller problem.
There are a couple more questions in here. Now, I know we got started a little bit late and we had a little bit of trouble getting started. And this is a question for Claudio, I guess. Can we, can she answer the questions in the Q&A?
Yes, I can.
Yeah, you can. Okay. So maybe what we'll do is have you type answers in there, and we'll handle it that way, and then move on to the next presentation so that we don't get into a late cycle, because I'd rather not do that. So thank you very much.
Thank you.
Virtual applause.
Thank you very much, everybody. Thank you very much, Christine. Thank you very much, Craig. Craig, would you be so kind to introduce the next presentation, please?
Yes, we'll be two presenters the next presentation. Bruno Favrenek is an ATM expert at EUROCONTROL's Innovation Division. He's been involved in ATM research for 30 years, working on subjects ranging from data link trials to ASAS, arrival management, and innovative arrival procedures, such as point merge, addressing fuel efficiency and environmental impact in the terminal area. He's also been involved in CESAR since the start of the program. And Rafael Christian is a data analyst at EUROCONTROL's Innovation Division. He's been working on ATM research for 20 years, notably on modeling and fast time simulation of trajectory management concepts. His current research interests include enhanced arrivals and departures within the CESAR program. So I'll hand it over to you two.
I would just like to add here, Rafael and Bruno, I guess you share the same presentation, so that will be the backup to the backup. The floor is yours. Thank you very much.
Yes, it's the same. It's the same. So I hope you can all see this slide.
That's fine. That's fine. This is
Perfect.
great. Thank you very much. We can hear you. The display is correct. Go ahead.
So I'm Bruno Favrenek, and together with Rafael, I will give you this presentation on the prediction of arrival delays in the terminal area 5 hours in advance with machine learning. So our motivation, why do we do that?
Just Bruno, just a second. My display shows 2 displays. One of them is presenter mode, and the other one in the back is the presentation. Oh, now it's great. Thank you very much.
It's better. Sorry about that.
Thank
So
you.
why do we do that? Our motivation is as expressed with participating airlines in our study, namely Air France, EasyJet, Ryanair, Swiss, Transavia, and Vueling. The motivation was really to improve the way weather is accounted for when planning for fuel. Today, actually, fuel planning processes do not account for weather destination in a very accurate manner. The result is a conservative and sometimes larger than required fuel loading. In terms, this means, of course, more fuel and an increased fuel consumption to carry this unnecessary fuel. On the other hand, we should take care that too low margins might result in actually a number of diversions. So within the present study, we have worked with the airlines to address this problem. And the idea was to provide a predicted airborne delay at destination as an additional input to the fuel planning process. When I say airborne delay, I mean the necessary additional time that is required to meter and to sequence traffic in the terminal area down to the runway, which may, if needed, include holding, but also past stretching. So the prediction would account for weather impact at destination and also the planned traffic demand. At this stage of our study, actually, we aimed for an initial proof of concept, and we are focused on intra-European flights at different prediction horizons for the dispatcher and for the flight crew. Our prediction is in the form of the likelihood that the additional time or the waiting time at TMA would fall within a small value, like less than 5 minutes, a moderate one, 5 to 10 minutes, or a high value, more than 10 minutes, computed over 30-minute time periods. And the prediction for the horizon time I mentioned is 4 to 2 hours before departure, which means 5 to 3 hours before arrival for a 1 hour flight time. We are focused on 4 European airports, London Heathrow, Dublin, Lisbon, and Zurich, which are actually very congested and in which then weather is expected to have an impact, measurable impact. So currently, of course, you have Ico regulations, and those regulations allow for contingency fuel loading using either fixed rates or statistical tools, statistical contingency fuel. And commercial tools exist also, start to exist at least, with custom algorithms to compute this contingency fuel. There were some studies as well on that. However, the statistical contingency fuel tools are not used by all airlines. Hence the request we had from the participating airlines, and our focus to look at arrival delay in terminal area as the main influencing factor with weather regarding the additional input needed for the fuel planning process. We conducted a thorough literature review, and it appears that there was a significant amount of research work from the mid-2000s relying on data science, artificial intelligence techniques to predict data such as airport delays, capacity, or arrival congestion. There were generally 2 main approaches, either to focus on the arrival capacity prediction itself as a building block to predict then delays, or directly focus on the prediction of delays. We opted for this second case, the direct prediction of delays, because in Europe, actually, we don't have systematically the accurate capacity variation figures available and easily. So that was our principle. The approach we took, actually, so we framed the problem as a classification problem. We developed a supervised machine learning model, and we used as input historical data, including traffic demand, weather in the form of a considered score to reduce number of features, but also wind direction, airport events that could affect capacity, the time of the day of the week, the quarter, and also the current arrival delay at destination. The output data is actually three probabilities. One probability to fall within one of the predefined classes, low, moderate, or high delay, as you can see on the diagram. So one of the advantages of having a classification rather than a regression is that classification provides a confidence level along with the prediction. That can be seen here. We have three probabilities. If the three probabilities are equal, then of course it's difficult to decide. But if you have got one of the probabilities that's much higher than the other ones, then it gives you a confidence, an insight on the confidence level you can have in the prediction. In order also to account for delay buildup, we have actually used traffic demand and weather data over a 5 hours period before the prediction. And the data set we used was data from 2013 to 2018 for the training and the validation, and the test set 2019. Finally, we can note that we used actually weather observation rather than forecast at this early stage of prototyping, because we wanted to discriminate between the weather forecast accuracy and the model intrinsic performance. Then, in order to benchmark the various options we developed and the model itself, we also developed a statistical baseline as a reference, which as input data takes the hour of the day of the week, and the quarter. Actually, the delays, the airborne delays were calculated from our archives, from our traffic archive. And the output is only one delay class. It's either low, moderate, or high, of course, corresponding to the average delay associated with the input. Again, the test data set is 2019, and the statistical data set used for this baseline is 2013 to 2018, same data. I will now leave the floor to Raphael to give you an insight of the model development and the measured performance.
Okay, thank you very much, Bruno. Well, we saw that all those models are all about predicting delay classes. So it's probably interesting to first have a look at the data. So looking at the training data set distribution of those data delay classes. So here you've got in the graph in the middle, you can see on the x-axis the arrival delay class. So low, 0 to 5, moderate, 5 to 10, greater than 10, so high delays categories or classes for the 4 different airports. So London Heathrow, Dublin, Lisbon, then Zurich. So in alphabetical order. On the y-axis, you've got the ratio. So what was the distribution, how much of those classes we could see in the data set. So we can see that for London Heathrow, the 3 different classes are pretty well balanced. We've got the same kind of proportion for all the 3 kind of delays in the data set. However, for the 3 other airports, this is very imbalanced. We've got much more low delays reported, more than 75% for all of them. And well, if you don't pay attention and you just give this data like that to a standard classifier and just measure accuracy, for example, you could have a model that could predict, let's say, all the time low delays. And for Lisbon, if you look at the accuracy of such a model, it will be more than 80%. And still, the model has learned nothing. It doesn't know how to distinguish between moderate delay situations versus low, on high delays versus moderate, etc. It didn't learn anything. So there's a risk that if you don't pay attention, your model might very well lean towards a majority class and not really learn the minority classes anyway, because it won't be penalized too much in making errors on those rare cases. So we have to find a way to actually manage that properly. So this is what we see on the next slide. Okay, so we did two things to actually manage this delay classes imbalance. The first thing was to increase the cost of the bad predictions for the moderate and high delay cases for the three destinations, Dublin, Lisbon, and Zurich. So a kind of inverse proportional cost for the rare cases. So in that case, the model would be penalized very much if it's making an error on the large delay cases compared to low delay cases. The second thing we have to pay attention is not to use a misleading metric to choose our models. And instead of using accuracy, which is a standard classifier metric, we'll be using what's called an F1 score. And this F1 score is actually combining two notions, precision and recall. And in practice, precision and recall usually at odds with each other. Usually when you have got a good precision, you generally have a bad recall and vice versa. So precision, for example, is imagine your model predicts 100 medium delay cases. The precision will tell you how much of those 100 predicted moderate cases are actual moderate delay cases. So it could be 70%, for example. So it's a value between 0, which would be very poor, to 1, which would be perfect. Recall, on the other end, is imagine you've got 100 large delay cases in real life. They're actually there. You'll see how much of those large delay cases were actually captured and predicted by the model. Let's say it could be 50. Then your recall is 50%. So the value goes from 0 to 1 again, like for precision. And the F1 score actually combines those two so that if it's going to be close to 1, it means you've got a very good precision and a very good recall, while it would be closer to 0, so a very bad F1 score, if precision or recall are closer to 0. So you really need to have both things to be good together. So in that case, we will avoid some ambiguities that might occur with accuracy metrics. So now that we've got a way to manage those imbalances, we could actually run a series of tests because, as Bruno introduced, we will be doing some supervised machine learning. So we'll train a classifier, but we've got a whole range of choices of classifier to look at. So we tested actually logistic regression, AdaBoost, a recurrent neural network, and random forest. And on our training sets, by doing our tests, we found that the RNN, the recurrent neural network, and the random forest had the best scores. So what we did is actually to pick the random forest between those two, because it had a nice feature, it had a nice characteristic to provide features importance. You know what was important for the random forest. And it's a bit more difficult for a neural network to get that information. And it also has got a faster training time, which is also good features. So now we're ready. We can train our random forest well, and now we can look at its features importance. What was important for the model? What was the higher link between the input and the delay output class? So here on that graph, you can see on the x-axis the importance score. So the importance score, it sums up the importance of all the input features together and sums to 1, a total of 1. And on the y-axis, you'll see what we're calling grouped features. Because, for example, if I'm looking at the one at the top, so the arrivals, we've got actually not only one input for the arrivals, but a whole series. We've got the number of arrivals 5 hours in advance, 4.5, 4 hours in advance, etc. So a whole series. So we just summed up the importance of all the arrivals features together to make up the importance of the grouped features arrivals for the model. And what we see with the different colors is the different importances of those input features for the different destinations. And the first thing we see is that basically we've got a very similar ordering of those features among the different destinations. So there are no strong differences of importances per airport. And then we can see that the most important factors is the number of arrivals. Okay, it's to be expected, but it's good to see it. So the number of arrivals is the first input features of importance to predict the delay output. Then it's followed by the number of departures. So arrivals and departures make up the traffic demand altogether. Then it's followed by the wind direction. And wind direction is probably linked to the current or what is the planned configuration of the runways, and therefore the capacity that might induce different delays. And finally, we can see our metric about the weather, so the consolidated score, and we can see it is the fourth item on the list for predicting the delays. The factors below those start to be of a lower importance. Maybe hour of the day can still be useful for London Heathrow and Zurich in pink, while for the other two, it's probably of a less lower importance. We were a bit surprised first to see that current delay was not that important. We were thinking that knowing the current delay, if it was very high, it could propagate still 5 hours later and provide some information. And it seems that in our case, it wasn't so much important. Okay, so we've got now an idea about what was important for the random forest model to do its prediction. Now we can have a look at what was actually the performance of the model on the different airports. So we can look at the next slide. I don't know if it's moving. Okay, thank you, perfect. So we'll start with our first airport, London Heathrow. So on the first line, I'm just reporting the macro F1 score. So first for the baseline, so we've got a score of 0.41, and the model had a score of 0.51. So it's an increase, so the model does better than the baseline, so it's an improvement of 24%. But of course, the F1 score might not be that intuitive to understand the performance just like that. We know it's better, but so what we do is actually to complement this metric with what's called confusion matrices. So one of the metrics on the left was the baseline, so 3 by 3, and the confusion matrix for the model on the right, 3 by 3 also. On the x-axis, we've got the predicted arrival delay class. Actually, when the model does a prediction, it provides, like Bruno presented, 3 probabilities for each of the delay class. And what we do actually is to tell the model predicted the delay class that has the highest probability. Whatever the value, the highest probability corresponds to what we considered here for those matrices to be the predicted arrival delay class. On the y-axis, you see the true arrival delay class, so from low to high, so from top to bottom. And if you focus on the first line, on the baseline, for example, when you read 0.04, it means that for all the cases of low delay, actual low delays, 4% were actually predicted, while 76% of the actual low delays were predicted as being moderate by the model, and 20% of those low delay, the actual low delays, were predicted as being high. So you can see the sum along this, each line makes sums to 1. So that's how we are reading actually the matrices. A perfect model will have only ones on the diagonal. So we have a perfect match between predictions and actual delay buckets, and 0 at everywhere else. Okay, so now we know how to read that. We can look at the results. So if you look at the baseline for London Heathrow, we can see that in most cases, the model predicts moderate delays nearly all the time. So again, so if the delays are low most of the time, the model will think it's moderate. Same thing for the moderate case, which is good, but also for the higher delays, in 58%, it will think it's moderate. Now, if we look at the model, there are 2 main improvements. One on the low delays, where you've got 53 of the actual delays well captured by the model compared to 4%, and 69% of the larger delay were actually well captured, so compared to the 41 of the baseline. So this is where the improvements lie mainly, because for the moderate cases, to the contrary, we've got something a bit less, which is really not so, you don't have a strong cut. It's kind of a distributed between low, moderate, and high, kind of hold together. So you've got a better way of seeing the low and high delays, not so much on the medium ones. So that's about the picture we can see about the performance for London Heathrow. Now we can have a look at Dublin. So a macro F1 score for the baseline, which is much lower than for London, so 27%, and the model is at 0.48. So still, we are not at a perfect score of 1, but it's a clear improvement. The improvement is clear because the baseline actually nearly predicts all the time low delays, and in 14–16% of the cases, moderate delays. So it's really very biased, of course, toward what's happening most, that is low delays. The model, to the contrary, is improving very much on the moderate cases. Well, you've got 61% of the actual moderate delays being predicted well. For the low delays, of course, we've got a degradation because the baseline predicts all the time low delays, so it captures them all, while the model is trying to do a balancing act with the other classes also. And for the large delays, the model again is just making a 21%, so it's not that good, but it's much better than 0, of course. And most of the time, it's kind of biased toward predicting moderate delays. So it probably couldn't disentangle the cases between large and medium delays. Okay, if we look now at the next airport, so Lisbon, we've got a very similar pattern that for Dublin. So again, a good improvement of model, 48% over the baseline. And baseline predicts all the time the same thing, and the model is shifting that correctly. Very similar to Dublin. And the last one, we can now look at Zurich. So Zurich, the baseline was 0.38, model does a bit better, so 0.48, so 26% improvement. And the baseline is doing a mix. Most of the time, it predicts low delays again, and in some cases, it does predict moderate delays and never predicts high delays. And the model for the case of Zurich is actually really improving only on the large delay cases, where you've got the 27% of the large delay cases actually predicted. While for the moderate delays, it's not really much better than the baseline. And for the low delays being predicted much more often, this is where the trade-off is made. And it's kind of similar, but even a bit lower. So we really gain here on predicting the larger delays. Okay, so this is a way to actually see the performance of the models, but it was a kind of a binary fashion, like mentioned before. Even if your highest probability, was 51%, for example, for the high delays versus, it's not the same as having a probability of 85% confidence of high delays to occur. You've got a confidence level attached to the prediction. So it could be very interesting to know when the model gives me a prediction, can I trust it or not? And when I've got a high confidence level provided, we actually checked if the model was right in being confident. And it seems that on average, when the model provided a good probability or high probability, indeed, the accuracy of the model was also higher. So that could be something useful, something to consider maybe in future application. If the probabilities are all low, okay, maybe it's not very useful, but if those are high, the model is confident, maybe you could trust them. And maybe we can now complement also those metrics with the last way of measuring the performance, because again, when you do some buckets, low, moderate, high, imagine you've got an actual delay of 11 minutes. So it's greater than 10, so it's going in the high delays category. But if you predict moderate, okay, you were just at 1 minute of the boundary of the moderate category. It's not the same as if it was 20 minutes and you were, far away from the moderate category. So here we just measured the distance between the actual arrival delay versus the boundary of the model's predicted class. And probably, so here on the graph, you can see again our full destination, the arrival delay classes on the x-axis and the error on the y-axis. And probably what's most striking is that for the larger delay, so greater than 10, especially for Dublin, Lisbon, and Zurich, we've got a strong difference between the baseline and the model. It's to be expected, but really here we can see it in a more continuous fashion compared to just the buckets we had when building the confusion matrices. So in a nutshell, this is about the performance we have so far in predicting arrival delays 5 hours in advance. And now I'm just giving back the floor to Bruno to show how maybe this could be used in actual operations.
Okay, let's try to also leave a few minutes for discussion if we can. So we have 13 minutes to go.
Okay. The last slide on results then. In addition to this overview of performances, we also explored the benefit mechanism. And we did that on a limited test case with 22 flights using data from airlines. You can see here on the diagram a series of samples, flight samples. The green histogram is the prediction from the model. So you can see the low, medium, and high probabilities. The actual delay that was recorded in our history is in blue, the blue line. And we did an estimate using the fuel planning data from the airline of the delay they had accounted for in their planning. And you can see on the two examples on the left-hand side, there are a number of correct confident predictions. We have a large probability for a low delay. The actual delay was indeed low, but the airlines did a prediction accounting for more fuel. That's the case where we could have a benefit, because then having this information as an additional input in the planning processes, they could have accounted for that. On the other hand, there are a few prediction cases where we had errors that will need to be analyzed, like on the right-hand side, where we predicted actually low delay with a large confidence, but the delay was actually large. So to conclude, we developed this random forest model for the prediction of arrival delays in the terminal area up to 5 hours in advance to improve the fuel planning processes from airlines. The model does beat the statistical baseline, and we have an improvement of 40% on average using this Marco F1 score, traditional performance metric. It's still not perfect, and overall, the main improvement we have still is on the large delay classes. We developed a small scale test to actually illustrate the potential benefits of the model. The future work we consider would be aiming at increasing the model performance, in particular investigation of the prediction errors, the cases where we have errors and the varied performance levels depending on the airports, because depending on the location, it's not the same level. Also identifying the cases where we have potentially maximum benefits compared to the current airline practices, which will involve then a comprehensive validation with airlines data. And finally, extending the scope to moderately congested airports and also a larger prediction horizon, in particular for long-haul flights. That's it for now, for the slides. Thanks.
Thank you, both of you. Excellent presentation. Do we have any questions from the audience? I don't see anything new in the chat, I don't think, or in the Q&A. The Q&A is a better place. No, actually, I do see a couple. Xavier Prats asks, I have two questions. One, you say you estimated the fuel planned by airlines to account for arrival delay. Could you please give some details on how this estimation was done? What input data from airlines did you have to estimate this particular fuel?
Okay, indeed, I can take that one. We actually had access to a few flight data from those airlines, and in particular, we had access to the fuel planning, including extra contingency fuel. For short-haul flights, the assumption was that the major part of this contingency fuel was due to terminal additional time in the TMA. And so by doing this, we back calculated, knowing the aircraft type, we back calculated the fuel corresponding to this extra time that was accounted by the airline in their planning.
Okay, thank you. Excellent. And a follow-up question, what about safety issues in case the airlines use your estimation for fuel planning and it turns out that you underestimated the delay?
Yeah, indeed, again, that's we didn't in this prototyping, let's say, part of the study, we didn't really aim at providing them a tool that can be used as is, but it's actually on their request an additional input that they can use. So of course they are still subject to any Ico regulation. They are still subject to any margin they want to take or any fuel policy they could have otherwise. Today already, it may be that some dispatchers are conservative, some others are less, and it happened in the past that there were a few diversions. So in that case, if we don't have enough fuel and there is bad weather at destination unexpectedly, you may end up with diversions if you are not cautious enough, even so still respecting the regulation, let's say, at the limit. So that's one of the questions indeed, and that's why we want to actually improve the model. But then the last word is still with the dispatchers and the flight crews.
Sure, that makes sense. Thank you. Do we have any other questions? Yes, we do. Nope, he says thank you.
Thank you.
So, I mean,
Thank you
I
very
might
much.
expand on that a little bit in the sense of, you know, what are they looking for in terms of how accurate, and this is probably impossible to answer, but it's a question that comes up a lot whenever you come up with decision support tools like this, right? Which is, how accurate does it have to be useful? Do we have some sense of that? In other words, have you made enough improvement here that they would consider adopting it as part of their methodology? Or do we have to do for more than that?
Indeed, it's, you know, part of the future work we identified under the bullet, identifying cases bringing maximum benefits. It's somehow it's hiding your question. It means we need a comprehensive validation study. Once we have an improvement in the model, we need to have much more data from the airline and their participation, their ops experts, their dispatchers and pilots, to ensure that we are actually helping them answer the initial question. And this includes, even if it's hidden somehow, it includes the fact that there is a need for a certain level of accuracy. Even so, they cannot formulate right now, they are not able to formulate it scientifically, let's say. But with a comprehensive validation, then we expect that this will be the kind of information that will resurface.
Makes sense. Thank you. Anyone else like to jump in? All right. Well, in that case, I will thank the presenters one more time, and both papers very interesting.